Let's start. Hello all. Let's start with our today's DSA and with this amazing playlist. See the visualizer by ChaiCode.com at dsa.chaicode.com. Use this link to get a 7-day free trial. Okay. Let's start. And today is nothing but heap. Okay. So now heap. And so what is a heap? A complete tree plus heap property shift up, shift down. Okay. If you search on heap, so heap has a specialized tree-based data structure used in computer science. Okay, or let's search it like this. Heap is a specialized tree-based data structure that satisfies the heap property and implemented as a complete binary tree. It is the most common use in efficient implementation in priority queue and hash. Okay, so what is heap? Heap is simply a data structure which uses a complete binary tree. Complete binary tree. And what is a complete binary tree? Complete binary tree is tree which at max two node or two child node, only the leaf node. So if you search complete binary tree, simple. A complete binary tree is a type of binary tree where every level is completely filled except the last level, which must be filled from left to right without any gap. Okay, so uh, this is actually the next question. Let's do it. So a complete binary tree is like this. Everything should be from or fill from left to right. Okay, so this is, if you do this, this is also, but this node doesn't have this second node, but everything is filled left to right. So whenever we fill, we cannot do like this. This is not a binary tree, complete binary tree. So every time when we are trying to fill, we have to fill it from the left to right. This is a complete binary tree. And heap is simply using this binary tree and using the properties. So what are the properties? And beyond properties, let's check how many type of heaps are there. Okay, so in trees, as we store values, so here we can also store values like 5, then simply goes 3, then take 2. This is simple heap. This is called max heap. And what is a max heap? A max heap is like every child node value is less than its parents. Okay, so here you can see 5 is greater than 3, 5 is greater than 2, and also you could do is like this. T, T, 30, 30, then simply goes like 20. So this is how, so every parent is greater than his child. This is called a maxi. And now what about minip? Minip just the opposite of the maxi, just the opposite. So in minip, if we, this is the parent, then the next should be this. Can easily say that every child value is greater than its parent's value. It is 60, so the parent is 50, the smallest. This is 80, it is 60, smallest. Okay, so when we search top from the heap, we always get, this is simply a min heap. So whenever we just pick from the top, okay, always in a heap we pick from the top. If we pick 50, if we pick 50 from here, you always get the minimum value of this, which is 50. So after we removing 50, the tree automatically the tree automatically form this operation. Why? Because we have to satisfy the min heap property, which is every child node value is greater than its parents. This is how it is work. Okay. Now let's dive to our today's question. Is this one? Let me show. Okay, and we can we can have a solution using sorting, but w- we can easily reduce our complexity by using a heap, and the code is not very big like this sort of simple code. Okay, so what is our question? First check it. Min heap of size is okay. Given an integer array and a value k, return the kth sorted order, which need not to be a distinct value. Okay, so what does this means? It means simply like, okay, this one. Suppose we are given 3 2 1 5 6 4. 3 2 1 3 2 1 5 6 4. Now, which is the kth largest element? Our k is 2. Which is the second largest element? So k is equal to 2, second largest element. In this whole array, which largest element? This 6. This 6 is the largest element. Okay. And what is the second largest element? This 5. So this 5 is our answer. Okay, if we go like this, 5 is our answer. Okay, how could we do this? Because for us the k is dynamic. K is not static that every time we have to just get the second largest element. K may be 3 4 5, any number. So we have to make sure that we just make it dynamic. So if we sort the array, suppose if we sort the array, it will become 1 2 3 4 5 6, and it says kth largest element, and k is largest element. So the last element is the largest element in sorting always, and the second largest element would be this one. And what is the index of it? Let's say size is n, so it is n minus 2. This is our index. So what is 2 here? It is simply k. It will become n minus k. Okay, so we have to do one thing. We have to do a sort and then return like add. First we have to perform a sort into the array, then simply return like array of n minus k. This is our solution. Okay, what is the time complexity? N log n. What is the space complexity? Big of 1. Why big of 1 space? Because we don't take any extra space. Why n log n? Because we are sorted. Okay, so the efficient sorting algorithm, if we use, we can reach up to n log n. So let's just write it. First, given array and k. So sort the array and then return array of n minus k. N minus k. So this is our solution. Very simple. Let's go and solve it. First we have to let's first sort the array. Simply sorting nums dot begin and then nums dot end. Then take the size of the array, which is nums dot size. Then simply return nums of n minus k. It should work. Let's run it. Yes, it's working. It's completely fine. It takes a very good time complexity of like, our time complexity would be big O of n log n, and our space complexity will become big O of 1. Here mention one thing also. Can we solve it without sorting? It is the most important thing. What we are given? We are given an array and a size k. We are using our heap concept here. Okay, so our heap concept simply told us to do one thing. Take a min heap. And what is a min heap? Min where each child node value is greater than its parent node. Okay, and we need a min heap of size k. K is given to us like here. I think we should take it. Just take a min heap of size k. So suppose this is our solution. This is our array given to us, and we are taking a min heap of size k. Okay, so let's take the heap like this. Okay, this is our min heap. Let's take image. So first we can easily with with this top function. Okay, so first check that if anything in min heap top, no, so insert this 3. Okay, insert this 3 rather, stop it. We take our min heap. Okay, so is anything into our min heap? Nothing, so add 3 here. So we add 3 into our min heap. Now this is our top. Now 2, is 2 greater than this top? Is this 2 greater than this top? If it is greater, then we take it, and if it is not greater, we don't take it. Is 2 greater than this top? No. Okay, first let's dry run it, then explain why min if, why not taking greater elements. So is this 2 greater than this top? No. Okay, go to next element. Is this 1 greater than this top? No. Is this 5 greater than this top? Yes. So add 5 here. Simple. Is this 6 greater than this top? What is the top? 3. Okay, so add 6 here. But now, what is our size of min heap? K. And what is K given to us? K is 2. Okay. And what is the size of our min heap? And how we calculate size? The number of node. How many number of node in this tree? 2. It's 3. And what we need? 2. So we have to remove the top. Just remove the top. Now 5 and 6. Okay, so just this is a min heap. And what is a min heap? In min heap, every child node value is greater than its parent node. We need a max heap. We need a max heap, not min heap. My mistake. Actually, we need a min heap. Let me give us. We need a min heap. So every child node value is greater than its parents. Okay, so in 5 and 6, which is greater? 5. So add 5 here. Add 5 here. So this is our node. Now 5 and 6. Now go to next element, which is 4. Okay. Now go to next, which is 4. Why happened? Is the 4 is greater than this 5? No. And at the end, when we complete our solution or our array, just return this top. This top now contain 5. And what is our answer here? 5. In this case, what is our time complexity? Big O of n. And what is our space complexity? Big O of k. See, we have k elements here. This is our time and this is our space. Okay, let's try run with this solution. But before, why min heap? Because in min heap, the child node value, this child node value is greater than this parent. Okay, so the parent is always the smaller value and the child node is always the bigger value. And we make sure the element contains only k size. Why? Because we find the highest is or the kth largest. Okay, so we insert k. Which two element we insert? The maximum two element. See, whenever we insert our value into the heap, we just check one thing, that is the value is the value is greater than or not. Simple. Does this two greater than the top? No. Then we just don't insert the things. Okay. So this is how simple our code is. And at the end we remain with k elements and our top will be always the minimum of those k elements and we need minimum of the k elements. So this is our solution. Okay, you can see the code here. Simply see the code here, but we have to make sure one thing: whenever there is like the size of the heap is become greater than k, we have to remove the top, the main thing. So let's see a visualizer here. See, we insert 3 here. Okay, see, we okay, it is something different approach. Let's write down our approach. It is most simple one. Given an array and a k, first what we have to do, we have to go through every element, like for I starting from 0 to n minus 1, every element, just or take a min heap. Simple. So add array of I to min heap. Simple. Add array of I to min heap. If min heap size is greater than and k, if any q dot or not pq, min heap dot pop. Okay, then simply at the end, what is our answer? Our answer is min heap dot top. So this solution may work here or maybe not work in this solution work in any code editor. Okay, solution. So if we evaluate it, maybe it run, maybe it doesn't run. Okay, it's running. So first we have to take a min. We have to take a min heap. And how could we take the min heap? Using priority queue in C++. Take a priority queue and we need an integer type. Also, let me write it. Let's take min heap. So this is how in C++ we actually take min heap. Okay, and how to take max heap? So this is how in C++ we take a maxif using priority queue. It is an inbuilt STL function of C++. Okay, this is simple maxif, and when we have to take minif, we first have to ensure our which type of data we want to insert, then vector at value type or data type, then greater of that data type. Okay, this is how we take. Okay, so if you say min heap in C++, it will always, this is like priority queue syntax, type, container, comparator. Okay, so this is how you take a min heap, simple, in C++. And it has every operation like push, top, pop, size, empty, simple. So this pop operation takes a login time. So our time complexity would become simple in log k, not in. Sorry, that is my mistake to say like uh, n. It is n log k. Why? Because the remove operation take login. So also the insert take login operation, but top take big of 1, size take big of 1, checks empty or not take big of 1. This is how we make sure. So this is maxif. We don't need a maxif here, we need a min. So first go through every element of the vector with which we are given. So num from num, okay, integer num from num set, then simply first push. So our min heap dot push num, and if and simply say if one condition appears, if min heap dot size greater than k, then simply remove the pop. So simply min heap dot pop. So this is our structure. Like we take and use pseudocode here. Like first we go through every element, add every element, and whenever it is greater than the min heap, we just pop it. Okay, and just return the min heap top. So simply at the end, return the min heap top. So this data structure will always do inside operations and make sure that it's correctly work. Okay, maybe a little bit. Let's run this here also. So see it. We just take 3, we insert it. Okay, simple. Then we insert 2, but this 3 is greater than this 2. This is not a min heap property. Okay, so we just swap it. Now it supports the min heap property. Then we don't insert any 1 here. Okay, then simply insert 5. Okay, then simply C, simple. Okay, and at the end we don't insert 4 here, and this is how it works. So this simple piece of code works everything in time complexity big O of n log k, and our space complexity would become big O of k. It is much more better than the previous one because previous one take big of n log n. Okay, this is how it works. Okay, the previous solution is also a good solution. There is nothing wrong about it, but here we mention one thing: can you solve it without sorting? So we use a min heap to solve it without sorting. Okay, this is the code, this is the solution, and go read about this thing use this platform, use this link to get a 7-day free trial, use this platform at dsa.chaicode.com. Thank you very much.